Otherwise, how is the equilibrium of this segment possible? For horizontal equilibrium, it is necessary that this segment should not experience any horizontal force. So, component of tension in horizontal direction here and component of tension in horizontal direction here should be equal. It is almost horizontal. The component of this tension in horizontal direction is, if the tension is T naught cos delta phi by 2. Dear students, here is our today's problem. A uniform rope of mass m and length L has been hooked to a ceiling as shown. This blue colored surface is the ceiling. At both the ends, the rope makes an angle of 45 degree with the ceiling. This is 45 degree at both the ends, right? This is a system which most of you have seen. You have calculated tension here and tension at this point. That kind of problem, literally every book has that kind of problem, and you all must have seen this problem. But what I am asking is very different. Find the radius of curvature of the rope at its bottom. At this particular point, what is the radius of curvature of this curved shape of the rope? That is the today's question. If you want to give it a try, please do it. Pause the video. Give it a try. I hope many of you can do it. Here I am solving for all of you who have not been able to do this. The first thing is, as you must be aware, that weight of this rope is being balanced by vertical component of tensions at the two ends. Here the ceiling is pulling the rope like this. Let us say this force is T. This is the tension. I mean, the rope is pulling the ceiling in opposite direction with same force T. Similarly, here also the ceiling is pulling the rope up in this direction with same force T, because it is a symmetrical situation. There is no reason why here it will be T1 and there it will be T2. It's all the same on both the sides. So, tension has to be same. Now, this tension has got a horizontal component. This one also has got horizontal component. The two horizontal components will cancel out. But this tension has got a vertical component, which is of course T by root 2, as you can see. And this tension also has got a vertical component, which is T by root 2. Please try to understand that this tension, direction of tension is tangential to the rope, and this angle is 45, means this angle is also 45. So, here it is T by root 2, here also it is T by root 2. So, the net vertical tension is T by root 2 into 2, that is T by root 2 plus T by root 2, and this must be balancing the weight of the rope. This must be balancing the weight of the rope. Otherwise, how is the equilibrium possible? Rope is in equilibrium, it is at permanent rest, which means this equation has to be true. From here you get the value of tension. That's fine, very good. Next, what is the horizontal component of tension? Obviously, horizontal component of tension, if I write it as TH, it is nothing but T cos 45 degree, which is T by root 2, which means it is mg by 2. So, horizontal tension is mg by 2. And do you know that horizontal component of tension in the entire rope is same everywhere? Do you know that horizontal component of tension is same throughout the rope? It has to be. For example, if you consider this segment of the rope, let us imagine that we are studying the equilibrium of this part of the rope only. Why this part of the rope is in equilibrium? Why it is not accelerated? Naturally, net force on it is 0. So, there is a weight of this part. Let us say mass of this segment of the rope is small m. So, weight is acting vertically downward, no doubt about it. We know that at this end the ceiling is pulling the rope with this force T, which we have already calculated, right? Now, for horizontal equilibrium of this segment of the rope, for horizontal equilibrium of only this segment of the rope, I am studying the equilibrium of this segment of the rope, it is necessary that this TH, that means horizontal component of T, should get balanced by the horizontal component of tension here. What I am saying is, If we consider this segment of rope, then this part of the rope is applying a tension force on it, and this tension, whatever its value is, I do not know the value, let us say T dash, but its horizontal component, the horizontal component of T dash has to be equal to TH. Otherwise, how is the equilibrium of this segment possible? For horizontal equilibrium, it is necessary that this segment should not experience any horizontal force. So, component of tension in horizontal direction here and component of tension in horizontal direction here should be equal, which means you consider any point on this rope, there is a tension, and the horizontal component of tension is simply equal to this much, which is equal to mg by 2. I hope you understand this. Now, the next step is to consider a very small segment of the rope at the bottom, very small segment of the rope, this red colored part. We will try to study the equilibrium of this very small segment of the rope, which I have colored in red. That will give us the radius of curvature of the rope at the lower point. Let us see how it can be done. Here I have magnified that diagram. I have just shown the red colored segment of the rope. This red colored segment of the rope, very small segment, which is extending equally on both sides of the lowest point. This segment that I have considered, the red colored segment that I have considered, is very small. It is just like a dot. It is just like a dot. Here it is a very small segment, as small as you can think of. Just think of a very small segment. So, it is a very small segment of the rope. Now, what is meaning of radius of curvature? If rope is curved like this, then what we are saying is this small segment is a part of a circle. Any curve, I have drawn a very poor circle, I would say. Let me rub it off. In fact, it's not looking good at all. First, I will draw a circle. In fact, this is a circle, and the red colored part that we are considering is a very small segment of this circle, right? Just imagine that rope is made up of many segments picked from different circles. Any curve is thought to be made up of large number of small segments of different circles. So, here this red colored segment of the rope, let us imagine, is made up of a small section of this white colored circle. Center of this circle is this point, center of this circle is this point. So, what I have shown here is this is the center of the circle, this is the radius of the circle, and this is what is known as radius of curvature of this curve at this particular point. Actually, the rope is like this. But the small segment of the rope can be considered to be part of a circle of radius r, and the radius of this circle is known as radius of curvature. So, we are supposed to find this radius r. That is what we are supposed to do. Okay. So, we are considering a very small segment of the rope, and this is the center of the circle. Which circle? The circle whose small part is this segment of the rope, and let us say this angle is delta phi. So, this one and this one both are delta phi by 2. Both of these angles are delta phi by 2. So, this small segment of the rope is subtending an angle of delta phi at the center of curvature. O is the center of curvature, and this is the radius. Now, we will study the equilibrium of this small red colored part. What are we going to do? The two ends of this red colored part are being pulled by the neighboring particles of the rope. This is the tension. I am writing it, okay, let me write it as T naught or whatever. Let us say tension here is T naught. Here the tension is T naught. Here also the tension is T naught. Of course, it is tangential to the length of the rope at that particular point. Let us say the tension is T naught. Now, do we know the horizontal component of this tension? Yes, it is known to us, isn't it? The horizontal component is known to us. Now, please try to imagine that because we are at the lowest position of the rope, our element is a very small element here. So, the tension here is almost horizontal. Can you see that? Because the tangent here is horizontal. It is almost horizontal. Why do I say almost horizontal? Because if I draw a tangent just here, it will be horizontal, no doubt about it. If I draw a tangent just here, it will be horizontal. But we are imagining a very small segment. This is not so large. You can see it clearly. That's why I have drawn it a bit bigger. But it is actually a very small segment of the rope. Okay, so this point is actually very close to this point, and this point is actually very close to this point. So tension here and here is slightly different than tension here, but only slightly different, and tension at this particular point is not exactly horizontal in our diagram. It is slightly tilted. It is tilted, though I have magnified the diagram, so it is looking a lot tilted, but it is not tilted this much. It is very close to horizontal, and therefore, because the tension here is only horizontal, the vertical component, if any, it is very small. If there is a vertical component of tension, which it is there, but it has to be very small, because this point and this point are really very close. So it is not wrong to assume that this T naught is nothing but actually equal to horizontal tension. It will be slightly different, but it will be only very slightly different. Let us imagine that it is same as horizontal component of tension at any point. What I am saying is tension here, here and here are not very different, but the direction of tension has slightly tilted by an angle of delta phi by 2, right? This is radius. If I draw a tangent here perpendicular to it, this is radius. If I draw a tangent, this is blue arrow. So the angle between this blue arrow and this white arrow is nothing but delta phi by 2 only. So the tension force that is acting here and here is slightly tilted by an angle of delta phi by 2. Just think of making delta phi by 2 as small as you please. Now, this particular tension here, blue colored arrow, is not exactly horizontal. It is slightly tilted. So it will have a very small vertical component, but it will have a vertical component. And what will be that vertical component? If you take the vertical component of this tension here, it will be TH sine of delta phi by 2, because this blue arrow makes an angle of delta phi by 2 with the horizontal line, exact horizontal line. So the horizontal component exactly is T naught cos of delta phi by 2. But delta phi being small, cos of delta phi by 2 is almost 1. What I am saying? The tension, horizontal tension is T naught cos of delta phi by 2, but delta phi by 2 is very small. So cos delta phi by 2 is nearly 1. Therefore, this T naught is nothing but TH that we have already calculated, mg by 2. mg by 2. Was it mg by 2? Yes, mg by 2. I hope you are understanding. So tension has got a magnitude of mg by 2, and its very small vertical component will be TH sine delta phi by 2. Similarly, here also it will be TH sine delta phi by 2. TH sine delta phi by 2. This is what the vertical component of tension will be. It is very small, no doubt. But this is the force which is balancing the weight of this red colored element. Now, the weight of that red colored element is also very small, because the angle delta phi is small. Anyway, what is length of this arc? Radius of curvature r into delta phi. So r into delta phi is length of red colored arc. Is lambda is mass per meter length of the rope. Then mass of that red colored element is this, and m into g, this is the weight. So obviously, as I am repeatedly saying that delta phi is very small, this sine delta phi by 2 can be written as delta phi by 2. Sine theta can be written as theta for very small angle. So that is what I have done in the next step. In place of lambda, lambda is mass per meter length of the rope. The total rope has mass m and its length is L. So m by L can be substituted for lambda, and you just cancel out delta phi, and you can substitute for TH also. TH is nothing but mg by 2. So, substitute for TH, which is mg by 2, and now you get radius of curvature as L by 2. So, students, it may be difficult to understand for many of you at this moment, but please try to pay attention. The diagram is misleading because I have drawn a very large arc, and this tension here is apparently at a very large angle to the horizontal, which it is actually not. It is almost horizontal. The component of this tension in horizontal direction is, if the tension is T naught cos delta phi by 2. So, for very small angle, delta phi very small, cos delta phi by 2 is almost 1. So, tension here is almost horizontal, that is all, is not it? That value of tension is same as the horizontal component, but at the same time it has got a very small vertical component, and that vertical component is essentially balancing the weight of that element, and this helps us in calculating the radius of curvature. So, I hope all of you have understood this. Thank you. Goodbye.